So this is the second part of the complex numbers 1 pack for AS Further Maths. In this pack, we're going to cover things like argand diagrams, modulus and argument, and most importantly, we're going to look at loci, which is something that you have met at GCSE, but gets a bit harder when we start introducing complex numbers. Argand diagrams are a way of visually representing complex numbers. So for real numbers, we use the number line. When we extend into complex numbers, we extend this into 2 dimensions instead. So along the x-axis, you have your real axis. Along the y-axis, you have your imaginary axis, and we can plot complex numbers on this argand diagram as though they were coordinates or as though they were vectors. So in this example 1a here, we're just going to plot some of these. So z1 is at 2 plus 2i. Just go along 2 and up 2 on the imaginary axis. Z2 is at minus 3 on the real axis, so 3 to the left, and at 4i up here. Z3 is at minus 1 minus root 3, so somewhere down here-ish. Z4 is purely imaginary, so we'll be on the y-axis. But minus 3i is down there. And Z5, that's purely real, so that will just be on the real axis. You can plot them as coordinates. Sometimes you'll see them joined to the origin with a straight line, but you don't need to do that. Coordinates is fine. From an argand diagram, then, we can calculate the modulus and argument of a complex number, which are useful things to have. The modulus is the distance of your complex number from the origin, so we just use Pythagoras to calculate that. The argument is the angle between the positive x-axis, or the positive real axis, and the line that you draw from the origin to your complex number. So we'll look at this in a sec. There are some kind of rules here that you can learn if you really want to, but my recommendation is that you always draw a picture of your complex number and use that to calculate your argument rather than trying to remember all of this. So we're going to calculate the modulus and argument for Z1 and Z2, and then Z3 to 5 are left as utilities. So first off, Z1. So Z1 is this point here. We can draw a line from the origin to Z1. The modulus is the distance from the origin to Z1, which we just calculate by doing the real part squared plus the imaginary part squared and square rooting it. Notice we don't include I when we're calculating this, so it's not 2i squared, it's just 2 squared, which will give you 2 root 2 in this case. The argument is the angle that this makes with the positive real axis when measured anti-clockwise from that real axis. So starting from the positive real axis and going anti-clockwise, it's this angle around here. This angle in here is the argument of Z1. We're going to use trig to calculate this. So the adjacent side is 2. The opposite side is 2. So we're going to use tan. So the argument of Z1 is inverse tan of 2 over 2. And we typically use radians to describe arguments. So we're going to say pi over 4 for this argument. For Z2, so Z2 is up here. The modulus, again, is the distance from Z2 to the origin. So that's 3 and 4. So 3 squared plus 4 squared. No, I'm not interested in the minus sign here. Doesn't make a difference whether it's negative. So just 3 squared plus 4 squared equals 2. The argument of Z2 is the angle that it makes with the positive real axis when measured anti-clockwise. So it's this obtuse angle around here. To calculate this, I'm going to work out the acute angle here, again, using tan. I've got 3 and 4 here. And then I'm going to take that away from 180, it would be in degrees, or in radians, I'm going to take it away from pi. So I'm going to do pi minus inverse tan. My opposite side from my diagram was 4. My adjacent side is 3. So inverse tan of 4/3. Pi minus inverse tan 4/3. 2.2. Please pause the video and have a go at Z3, 4, and 5. I will reveal the answer in a minute. So answers to these are on here. So a modulus of Z3, you should get 2. So the argument of Z3 is down here. If it doesn't specify, you could give the reflex angle from the positive real axis, but usually we'll measure this angle. So usually it'll be between pi and minus pi, like it said here. If we're going clockwise instead of anti-clockwise, we'll give our angle as negative. So if you calculate this angle in here, we'll give this as a negative argument of minus 2/3 pi. Z4 is just down here, so go modulus of 3, and the angle that this makes with the positive real axis is this one here. It's 90 or pi over 2, and it's negative because it's gone below, it's gone clockwise. And for 2, it's got a modulus of 2, Z5 is over here. You could either say plus pi or minus pi, but typically we include pi. So we're going to say argument of Z5 is pi. Complex numbers on the Argand diagram work a little bit like vectors, so work exactly like vectors actually, which will be really important in the if you do full further maths in the second complex number pack. We can demonstrate this here. So for Z, we've got 3 plus I, so going 3 to the right, 1 up, this is Z. For W, we're at minus 3, we're down here. And it's very easy to calculate Z plus W. So Z plus W is 3 plus I plus minus 3 I uses minus 2I. And easy to calculate Z minus W for 3 plus I minus 3. It's 3I. So 3 minus 3 gives me 6. I minus 3I gives me 4I. I've got Z and W already plotted on the diagram. Z plus W we had was minus 2I down there. And Z minus W is at 6, 4. It wants us to do them as vectors as well, so I'm going to draw straight lines from here. So I've got 1 here, 1 here. Z looks like this one. And W is down here. Notice I've put arrows on there as well. From here, you can see how these vectors work. So Z plus W is down here. To get from Z plus W, I'm going from the origin to Z along the green line. And then if I add in the red line here from W, that will take me to Z plus W. So works like vectors there. Similarly, if I do Z minus W, so I go the opposite way along W, I will get to Z minus W up there. Have a go at this U-try question down here, and I'll reveal the answer in a sec. The calculating these moduli shouldn't be hard. So modulus of Z, you get root 10. Z plus W, you get 2. Modulus of W, you get 3 root 2. And Z minus W, you get 2 root 13. Obviously, we can say the student isn't correct because the modulus of Z plus the modulus of W is not the same as 2. In actual fact, it's true that the modulus of Z plus the modulus of W will always be greater than or potentially equal to modulus of Z plus W. That's because these make a triangle. If we go back and have a look on here, the Z plus W is here. So in a triangle, the modulus of Z, the green one, plus the modulus of W, the red one, has to be bigger than the length of these added together, has to be bigger than the third side of the triangle. The only way that they could be equal is what would be if they were along the same straight line. Otherwise, those lengths have to be bigger than the third side of the triangle. Bit tricky for C. So if you calculate the argument of Z minus W, you should get 0.588. The point that it's trying to make here is obviously this is the angle that z minus w makes with the origin. But what this also is, if I get rid of a couple more of these lines, actually, this vector here, z minus w, is the same as the vector between z and w, and it's also the angle that that makes with the positive horizontal there, which is useful sometimes as well. So that's what it's trying to say there. We'll come back to this in the loci section.